So in the first lecture, we saw some basic derivations of the radiative transfer equations, understood the implications of the various assumptions, and what is the solution of the specific intensity under different scenarios. We understood about optical depth, we understood about the emission coefficient and the absorption coefficient. Today, we'll be briefly reviewing some of the emission mechanisms which give rise to the J nu term that we saw yesterday. Now, at the outset itself, I must tell you that I will touch upon synchrotron emission, Bremsstrahlung, and if time permits, Compton. All of these require a lot of mathematics, like on-board work, and it is not really possible to give you the entire gist of things in one lecture. So the basic thing is, do not focus on the mathematics of it. Try to understand what a given process implies, what is the physics behind it, and that should help you get going, at least for the rest of the school. And hopefully, as you evolve more, go through your master's and PhD training, you'll encounter these theorems more and the physical processes more and understand these in a much deeper way. Also, to go into this, there are some prerequisites that you have to go through. One of them is the electrodynamics, so fields of moving charges. And again, these take several lectures to go through. I will just give you the basic glimpse of what is required from this formula that is seen on the screen. I will not tell you how it comes because you will go through the full scale of retarded potentials, etc. when you go through your master's training. And of course, people who have already gone through this would know anyway. So the basic idea is all sorts of radiation is coming from charges that are accelerating. Okay, so if you look at the solution of the, here's the pointer. So if you look at the solution of the electric field, what this solution gives you is the electric field of a moving charge. Now you can see, and again, just take my word for it, that this is the expression that you finally get. The bracket retarded means the figures should be computed at a time that is R by C, so at an earlier time than which the charge's current position is, because the radiation would have started from here and reached the observer by the time the charge would have moved here. So we compute things at this point when the radiation had first left the charge and coming towards the observer. So you can immediately see there are two terms here. One is E proportional to 1 by R square. Now if there are no motions of the charges, these things are zero, the retarded time is same as the current time. This becomes very much equivalent to what you have in a static potential. If there are motions, if there are constant motions even, and no acceleration, even then you get something like this. This term goes out because there's a beta dot, this acceleration term there. So in constant motion, again, if you just consider, for example, if you change your reference frames, you can go to the instantaneous frame of the charge, then you would not see any radiation. So there is no energy loss from the system. But as soon as the charge's velocity is changing, this beta dot term comes into effect. And you can see that the electric field component of this term goes as 1 by R. Okay. Now, I guess most of you have some basic understanding of what is the Poynting flux. So that is the energy carried by the electromagnetic radiation per unit area. And Poynting flux is E cross B. And B is again just R cross E here. So essentially in terms of magnitudes, if you just do order of magnitude calculation, Poynting flux will be proportional to E squared. And then the Poynting flux for this term becomes proportional to 1 by R to the power 4. Now this is per unit area, and if you multiply it by area, then the Poynting flux from this term actually decreases with space. If you go to this term, the Poynting flux is proportional to 1 by R squared. The area term will give you another R squared. So Poynting flux is constant. So this is the radiative part of the electric field, where the radiation energy can travel up to infinite distance. So whenever we talk of understanding what is the emission mechanism behind any given particular situation, this is the term that we have to focus on. So for a given particular scenario, we have to understand what is the acceleration vector for that particular configuration, and then compute this term, compute the Poynting flux, we get some expressions of the power. Once we get the expression of power, as I had said earlier in the previous lecture, we can have a handle on the emission coefficient and the INU. That is the basic gist of it. I have all these figures here. This is very nice pictorial depiction of what happens, how the field changes as the charge is initially traveling with a finite velocity, and then it suddenly stops. Okay, so maybe it's just worth spending 1 minute on this. So initially when the charge is traveling, and then at x equals to 0, it just stops. There is some deceleration and it stops. So deceleration means there is acceleration. So the fields outside this layer of where the change is taking place, they will point to this location x1, the virtual location where the charge would have been, because these regions does not know that the charge has stopped moving. But for these regions, they know the charge has stopped moving, so it becomes a static, standard electric field lines of a static charge. For these are the field lines of this quantity here, where the charge was moving. So this zone is actually the radiation field that is traveling out and informing the locations here that something has changed here. So the electric field is changing. So it's a very nice pictorial way. You can look up Ribicki for more details about this. Just wanted to show this because then it's important to understand how we compute the power. Again, I already alluded to the Poynting flux. And I will again, as I said just now, the second term is the radiative term of the electric field. So we'll just ignore the first term because that just dies out. So if you take the radiative term after some basic algebra, you compute the Poynting flux. Poynting flux is proportional to E rad square. And you put things in, you'll find that the expression of and Poynting flux is per unit area. So Poynting flux, you can convert the area term into r squared d omega is the solid angle and r is the surface of the solid angle. Again, I will provide all this PDF, so you may not need to take notes, but feel free to do so. So if you compute, so this is, if you want to compute the power per unit solid angle, you get an expression something like this. This is something very important to understand. Okay, first, before I go into it, if you integrate over all solid angles, the total power emitted, power is energy per unit time, you integrate over solid angle, you get something like this. This is 2q square u dot square divided by 3c cube. Very powerful formula. It's called the Larmor's radiation formula. And we will use this soon in understanding the total emission from a charge in a given scenario. But now let us come back to this. So it is a power per unit solid angle. You can see there is a sine squared theta term because of this cross product that was here. What is the sine squared theta? If this is the direction of the acceleration vector, theta is the direction of the observer or the direction of the solid angle towards which we want the radiation. So this sine squared theta term gives you the distribution of power in terms of solid angle in a two-lobed dipole kind of shape. So the power along the acceleration vector is 0. Power perpendicular to the acceleration vector is maximum. And it traces out this. So if your line of sight moves around with theta, it will trace the intensity of the power being emitted in this way. It is important to note how this distribution of power in terms of solid angle is shaped, because as soon as you go to moving charges or relativistically moving charges, these all dipole pattern will change. I'll show you in the next slide. So two key takeaway things. One is the Larmor's formula, which is 2q square u dot square by 3c cube, which tells you that if you know the magnitude of the acceleration, you can compute the total power being emitted. And the other point is this dipole pattern of the power being radiated. Power per unit solid angle, dp d omega. Now, I told you the Larmor's formula earlier, so that was for a non-relativistic particle. So what do we do for relativistic particles? Again, all the approximations earlier assume some sort of a non-relativistic approximation in them. But before going into full-scale relativity, we can easily play some tricks and find some Lorentz invariant form of these expressions. Again, I've sketched out the derivation here. It's quite trivial actually, because you take the acceleration vector you would make a dot product with the proper velocity, and you will find that the a dot u is actually a constant. So then the acceleration vector, you can take it for an instantaneous rest frame that is state static with the charge, and you can write it in terms of this. So this is the same Larmor's formula, but written in terms of the 4 acceleration here. So u dot is the 3 acceleration, and a is a 4 acceleration, but in the instantaneous rest frame, this becomes equal. Now it becomes a Lorentz invariant form. Again, just follow this instruction. I don't have much time to spend on all of this, unfortunately. And then once you have this in the instantaneous frame, you come back to the lab frame. And one can show that the acceleration vectors parallel to the direction of motion and perpendicular to the direction of motion scales in this way. This is just basic Lorentz transformation. Put all of those in, you get this expression for the pointing, for the Larmor's formula, for the power from the Larmor's formula, which is 2q squared by 3c cubed. This remains same, but the u dot squared transforms into gamma 4 a perpendicular squared plus gamma squared a parallel squared. Why am I showing this? Because as soon as I go to something called synchrotron radiation, I will need this formula. Again, no need to right now in this lecture hall understand the specifics of the derivation. What you should take away from this slide is I have something called the Larmor's formula that relates the total power emitted to the acceleration in non-relativistic frame. After doing some relativistic transformations, I get a relativist formula that is correct with special relativity, and this is how it looks. So the perpendicular component of the acceleration and parallel component of the acceleration contribute to this term differently. So in a situation where the parallel component of the acceleration is 0, then I will just have contribution from the perpendicular component. And this is what we would need right now. Again, I told you about the dipole pattern formula. This is again becomes very important. This is the concept of relativistic beaming. Now, to understand beaming, you must have heard it always now that particles moving at relativistic speeds have the radiation pattern directed towards the direction of motion. What does that mean mathematically? Okay, so these are the angle transformation formulae for relativistic transformations. So what you can see is for theta prime equals to pi by 2, that is in the instantaneous rest frame of the charged particle, if it's pi by 2, you go to the lab frame, the angle transformations is sin tan theta c by gamma v or sin theta 1 by gamma. So if the particle is moving at highly relativistic speeds, gamma 100, gamma 1000, gamma 10 power 4, the sin theta is 1 by 100, 1 by 1000, 1 by 10 power 4. So you can see that sin theta can be approximated then as theta. So theta equals to or twiddles 1 by gamma. So this is what it means. Remember what was the initial approximation? It was that at theta prime equals to pi by 2. So suppose now in the instantaneous rest frame of the charged particle, the emission is isotropic. Okay, so this is the rest frame. All isotropic emission, spherically symmetric. Now I take these pi by 2 angles. All of this radiation from here to here will be beamed in the forward direction within a cone of 1 by gamma. It does not mean that the other radiation, there is no radiation outside of 1 by gamma, there is, but the radiation falls off very drastically. Interesting point, put in theta equals to pi in this formula and see what you get. Relativistic beaming would give you the naive idea that everything, all the radiation is in the forward direction. Put in theta equals to pi and see what you get. What is important to note that it is not just one particular angle, but the distribution of radiation along that angle. That is what is important. Again, for your own sake, put theta equals to 120. See what this angle becomes. You will feel most of the field lines are bunched in the forward direction. It will be outside of theta 1 by gamma, but very close to these two cones. But the takeaway point is, if you have a spherical emission like this, it gets bunched in an angle of 1 by gamma along the direction of motion of the charge. Okay. Now, I just showed you what is the dipole pattern formula. So the total dp d omega distribution, which is the dipole pattern. And if I go back a few slides, I'm talking about this. So if in the rest frame of the charge, this is the emission pattern, how will that look for a relativistically moving charged particle? Again, I'll not go through all of these. It's there in Ribicki, but just visually try to understand how this dipole pattern is changing. So again, the two lobes of the dipole will be crunched in the forward direction. Again, the peaks of this dipole will have an angle of 1 by gamma, because the peaks of this dipole here is pi by 2. So peaks would be at an angle of 1 by gamma. In a different scenario, so this is when the direction of motion is along the direction of the acceleration vector. So this is the acceleration vector. The charge is also moving along the direction of motion, acceleration. What happens if the charge's motion is perpendicular to the acceleration vector? Now, dipole pattern would be perpendicular to the acceleration vector, so the lobes of the dipole would be directed along the charge. So what will happen now is, this lobe will remain, again, get crunched, so it depends on what is the initial distribution of theta. This lobe will get crunched into 1 by gamma, but this back lobe will bend forward in terms of the angular distribution. Okay, so this is how it will look. And again, this is what we'll need in the next slide. Not the next slide, in a few couple of slides. So again, the takeaway point from this is relativistic beaming shows you that when a charged particle is moving in a particular direction, the emission, although from the instantaneous rest frame has some pattern, the major fraction of the emission would be directed along the charged particle within a cone of 1 by gamma. That does not mean that there is no radiation outside it, but that is what we will need to focus on, because the most radiation is focused there. Now we come to motion of charges in magnetic field. I'm slowly building up to something called synchrotron radiation, which you will need a lot when you do radioastronomy. So I will again not go through the derivation of these equations. This is the equation of motion in special relativity. So force equation, special relativity. The derivations are there in Ribicki in chapter 4. So in this case, all of you have done basic electrodynamics, so you know the gyration of charges along magnetic fields. And dropping the gamma, this is exactly how the equation looks like. If the charge is now moving at relativistic speeds, you have m gamma dv dt equals to q v cross b by c. And for now, the acceleration component parallel to the velocity is 0. Forget the parallel component. So assume that it's not a helix, it's just a gyration along the magnetic field. So you get the perpendicular component of the acceleration vector. So now you already have one term in the Lamar's formula that we need. There is no acceleration in the parallel component. So coming back to the Lamar's formula, we immediately drop this term, and just from these basic equations, we can find out the total power being emitted by the electron. So this will be most likely electrons that are gyrating along magnetic fields, because electrons are more easily excited to very high speeds due to different acceleration mechanisms. A few things to be noted here. One is the Larmor frequency. Again, these are basic things that you must have already learned in your electrodynamics. What is the frequency of gyration in a non-relativistic regime? For relativistic Larmor frequency, it is charge times magnetic field by gamma times mass times c. So m here would refer to the electron mass, me. And there is a neat way of writing this in terms of the classical electron radius, which is e squared by me c squared. Okay. So again, this is just a jumble of formula. What is important to note here is, how does this formula depend on some terms? So firstly, note that it is proportional to square of the magnetic field. So if the magnetic field of the region from where the emission is taking place is high, the power being radiated also increases, which also means that the electron will lose a lot more energy for a region with high magnetic field. And this has serious consequences of how the spectrum of electrons change. I'll come to the spectrum soon, but keep this in mind that it's proportional to B squared. It's also proportional to gamma squared. So if you have a distribution of electrons, all with different sort of energies and different Lorentz factors, Lorentz speeds, then the more faster electrons will lose more energy at a faster rate. So what that means is the spectral, if you have say an initial distribution of electrons, so the electrons as a function of energy, let's say a spectrum of electrons. So if the spectrum electron is suppose a power law, it's just a straight line. Again, these are more advanced concept, but you might need this at some point. The spectrum is a power law like this. These regions here are cooling or losing energy faster than these regions. So all of this will change, but if it was same, if it had no dependence on the gamma, then the spectrum would have become like this, just a drift. But now since this is losing faster, it becomes something like this, because the higher energies are losing faster. So the spectrum curves and decays, and this has very serious implications, and you can use this kind of implications to compute certain characteristic properties of the source which is giving out this emission. Beta perpendicular square. Now you might think that, okay, these are relativistically moving charged particles, so beta is close to C, so why bother? Why we bother is because it is beta perpendicular. We have to compute the perpendicular component of this quantity. And as soon as we do that, we have a sine alpha term. So the velocity direction with respect to the magnetic field. If sine alpha is 0, then you do not have radiation, because then it is not gyrating, it's just moving along the magnetic field. Okay, so these are again just basic definitions. So what is the total average power? You integrate over 4 pi, etc. What is interesting here is you can recast, so integrate over the solid angles and divide by 4 pi. So essentially solid angle means sine square alpha here. And divide by 4 pi, so it is the average power emitted over the entire solid entire sphere. And you can recast this into this equation where UB is just the square of the magnetic field divided by 8 pi. Now square of the magnetic field by 8 pi is associated with the energy density of the magnetic field. So what is important again to take away from this relation here is the total power, average power radiated by the electron, averaging over the all solid angles, is proportional to gamma square and proportional to energy density of the emission, of the local magnetic field. When you go to inverse Compton, and I don't think I'll have time to show that today, the total power emitted again retains the same formula, same form, exactly same form, except for the energy of the magnetic field, we replace it with the energy of the background radiation field. So when you consider total energy losses of a system, we often write it as something like this. 4 by 3. Beta square we remove now because beta square is almost close to C. Then UV plus U, say R, which is the radiation field. And in say a typical example would be scattering of these energetic particles with a background cosmic microwave background, the background radiation field. So the energy density here would be the background radiation because of the CMB. It can also be basic energy radiation distribution due to any background system, for example, background starlight, etc. Now, we are slowly inching towards understanding what is synchrotron radiation. So these are charges that are moving at relativistic speeds around a magnetic field line. Now, this is where, again, I will not derive, of course, synchrotron radiation because it's extremely complicated. Give you some brief idea of what this implies and what is the type of emission that is happening here. So, since the charge, as I said, is beamed along a cone of 1 by gamma. So, if the charge is here, So suppose this is the direction of the gyration, and this is the observer. Okay. So if the charge is at this point, this is the instantaneous velocity vector. The emission would be along this cone. The observer is not seeing anything because there is nothing coming towards the observer. Only when the charge, so if this is the instantaneous vector, only when the charge's cone velocity vector is such that the cone starts entering the line of sight, only then will the observer see something. And as soon as the charge leaves this cone, this charge's cone of emission, this cone is 1 by gamma. As soon as it leaves the observer's line of sight, the observer doesn't see it. So the observer sees any emission from the charge only for a small duration of its gyration period. So essentially what the observer sees is a pulse of emission. If you just keep looking at the charge comes, you see a pulse and then it goes away, and then a pulse and then goes away. So what is the width of this pulse? You can do some very quick back of the envelope calculations. I'll sketch it for you. This is derived in Rybicki in a more elaborate way, but you know the total gyration frequency. So what is the time that the charges spends between these 2 points? So this is del theta del t equals to omega b. Delta t is delta theta by omega b. Now this delta theta, so this is the cone of this rotation. This is 2 by gamma, because 1 by gamma, 1 by gamma, the cone. So it's 2 by gamma omega b. This is the time the charge spends between these 2 points. This is not the time interval of the pulse that the observer sees. Why? Because as soon as the charge enters here, the observer starts seeing some radiation. So radiation has some finite travel time between these 2 points. So what we should consider is, suppose you have a straight, so I'll approximate this as a straight line here. This is a straight line. This is point 1 and point 2. Sorry. And the charge's arrival at this point is T1. This point is T2. But the observers will see at different arrival times, because as soon as the charge arrives here, this radiation will have to travel this path here, this path length here. Let's call it S. Okay? Or S is V by C, approximately the uniform velocity, V by C. And then there is extended distance to the observer. So the arrival times is, for the radiation from here to the observer is T2 plus L by C, and from here to the observer is T1 plus not V by C. Yeah, it is V by C. Yes.
S by C.
S by C, that's right. T1 plus S by C plus L by C. Approximate just a constant linear velocity. So this is, this is T1 and this is T2, yes. So you have to take the T2 arrival times and T1 arrival times. T2 arrival time is this, minus T1 arrival time is this. You'll get an expression here. Try it out. You have to use one approximation, which is 1 by V minus 1 minus V by C. You'll get something like this. Again, I unfortunately don't have time for all of these. But delta T arrival is delta T interval between these 2 times, 1 minus V by C. It's actually a Doppler formula. You can approximate this in terms of the gamma for a high gamma, for a large value of gamma. And then you get the additional gamma cube there. So we already have 1 gamma here. This will give you 1 by gamma square. And this is that is what you get as 1 by gamma cube. Rybicki derives it a bit more sophisticated, elaborate way. You find the total arc, the time spent in the arc, etc., etc. But just to give you a basic hint that this is the pulse width. Now, if you have a pulse like this, let me go to the next phase. Okay, a lot of complicated equations. You don't have to go through this in full. Just I'll tell you what is the takeaway point of this. So what this shows you, this entire region of calculation is, if we want to find the spectrum of the radiation, what we must understand is how the Fourier transform of the electric field is derived. How do we arrive at that point? We have some basic definition of the electric field and its Fourier transform. We have the Poynting flux, which is the energy by time per unit area, which is proportional to E squared. Again, this is something that we know. Then we integrate over the total time, because we want to find the total energy within this pulse width. This now you can replace with the Fourier transform using Parseval's identity. And again, you divide it by the frequency, then the spectrum now, energy per unit frequency, becomes proportional to the magnitude of the Fourier transform. And you can go through this in much more details later, but this is what is important. Why I'm saying this? Because as soon as we go to Fourier transforms, and if it's a pulse, we know how its shape would look like. For example, if it's a finite pulse like this, of width t, the Fourier transform in the frequency space will look like this, with a width of 1 by t. So the pulse width is short, the Fourier transform will be broad. So what do we have here for this particular system? We have a very short width. This delta t is proportional to 1 by gamma cube. And the gammas can be very small, very large. So the pulse width can be very small. Take the Fourier transform. So as you know now, the Fourier transform gives you some idea about the spectrum or the spectral distribution of energy as a function of frequency. So now itself you understand that the spectrum would be quite broad. So there's a broad range of radiation over different frequency. But this also gives you, if I go back to the previous slide, does it change now? Previous slide, the characteristic width of this pulse in the frequency space is 1 by t. Okay. Again, just from very basic simple arguments, I'm not doing any elaborate mathematics of the Leonard-Wichet potentials here. You can understand that we can have a characteristic frequency. So frequency will be broad. I'll show you the spectrum just now. But there will be a characteristic frequency beyond which the spectrum will start dying out. And this characteristic frequency is 1 by t. Again, we have put some constants in front, preempting some of the actual mathematics that will come in. So this is called the critical frequency of the synchrotron emission. Critical frequency is gamma cube omega b. And let me see if people are paying attention. What is the total dependence on the Lorentz factor here of the critical frequency? Any raised hands? Yes, who said that? Yes, because omega b has a 1 by gamma then. Good. So people are not asleep. It's 10, 11. So now you know that the critical frequency is proportional to square of the gamma and the sine alpha and the magnetic field. Linear proportional to magnetic field, square of the gamma and sine alpha. Important things to remember. Because the critical frequency characterizes the spectrum and the frequency. So if you want to observe the synchrotron emission at a given frequency, it will tell you what is the intensity that we would expect, because that is what the spectrum is. The full-fledged solution requires you to calculate all the acceleration vectors, etc., etc. Will not go into it. I just wanted to show you this slide because this is how you do it. You actually calculate the trajectory of the particle, then calculate the n cross beta, everything together. This is possible, but it requires a bit of algebra. Why I'm showing you this slide is because now we'll have to define two directions. So if n is the direction of the observer towards which we want, then we have two, the electric field will be perpendicular to it. Now we'll have two vectors here which are perpendicular to the direction of the observer, because this is how the oscillation the electromagnetic field is oscillating perpendicular to the observer. But you can have two polarizations. Here in this convention, when you derive the synchrotron formalism, one vector is perpendicular to the direction of velocity of the charged particle and the direction of the observer, which is called the epsilon perpendicular. And naturally the other vector, which we call epsilon parallel, but it's not really parallel to any of these quantities, but it is parallel, lies in the plane that defines the n vector, the direction cosine towards the observer, and the velocity of the instantaneous velocity of the charged particle. So these two vectors are important because when I show you the next formula, we will derive the formula, the total emission for the E perpendicular and E parallel, and then sum it up to get the total emission. And this is exactly what it does. This is the energy for the perpendicular component, energy for the parallel component, with some front constants in front, and it is proportional to these integrals. X is, you normalize the frequency with the critical frequency. That's how we define these integrals, and some Bessel functions. How you derive it? You have to go through a lot of mathematics, but you have to take my word for it for now. So this is the power perpendicular, power parallel. You have these two fx and gx functions. And the total power then is just sum of these two. The gx integrals go away. But the gx integrals are important if you want to understand the polarization. So coming to the basic synchrotron formula. Synchrotron formula is essentially guided by the nature of this integral over here. And how does this integral look like? It looks like this. This defines the spectrum of the synchrotron radiation. So this is from the very old paper, Ginsburg and Sirovatsky, I think 59, I forgot, was 59? I forgot the exact citation, but I put in the slides. Science, do you remember Ginsburg, Sirovatsky? Okay. So this is how the spectrum looks like. So this is omega by omega c, this is the x. And you can see it peaks at 0.29 omega by omega c. So this is very nice. First of all, what I claimed in front is true, that the spectrum is pretty broad. It is not a spike. And once you know the omega c, you know that the frequency or the emission would peak at close to the omega c value. It's 0.29 omega c. Now, at what frequency you observe, that will define where you lie on the spectrum. This is the second last slide of synchrotron. I have to go through the next one. As I said, this is for a single charged particle. But charged particles can have a distribution like this. So in typical systems, these electrons, these energetic electrons which have been accelerated to very high energies, normally you will have electrons lying around in thermal medium. Why would they have so high Lorentz factors? That's because they have been accelerated. Something has driven them to such high energies. The usual mechanism is particle acceleration. There are various methods of particle acceleration. You pass through a shock, the charges go back and forth across the shock and tap energy from the shock, and then they get energized. You can have magnetic reconnection, where two opposite magnetic field lines start to join at one point, and they dissipate at the region of the joining, and they dissipate and get converted to thermal energy. And any charged particle getting trapped here will then get accelerated. There are various mechanisms, but after this acceleration mechanism, typically what we find is the particles have a power law distribution. And we are talking of leptons here because it's harder to accelerate protons. But it is not true that we cannot have proton synchrotron. For very highly energetic systems, perhaps we can, but usually we have electron synchrotron or leptonic synchrotron, positron synchrotron as well. So we have this power law distribution. Now forget the fact that the power law will change. Forget that for now. This is a more complex topic. So if you have a power law distribution, you know the power for one electron. All you have to do is integrate over this distribution function. The integrate over gamma. Now this becomes slight bit of algebra because this function is a function of x, which is omega by omega c. But omega c has a gamma dependence in it. So you collect all the terms together, remove the gamma, and then transform these equations in terms of this x parameter, and then becomes a standard integral which can be tabulated and performed. What is interesting here is this is just an integral. It can be performed with some limits. Note how the power depends on the frequency. So for electron distribution going as e to the power minus p or gamma to the power minus p, the frequency is minus p minus 1 by 2. Very powerful. What it shows you that if you observe the spectrum of synchrotron radiation, now forget this curvature part, if you are in the first part here, if you observe a power law distribution of the synchrotron, just from the observed emission, you can infer what is the particle distribution that is giving rise to the synchrotron emission. Again, then you can go and compare what is the physics of this particle acceleration in the first place. Very powerful formula and very interesting. So this is the synchrotron. I think this is the same thing it's just how you evaluate the integrals, and this is the result of the evaluation. In a more complex spectrum like this, you cannot use the simple power law. You can integrate numerically all through the entire spectrum. These are synchrotron maps. For example, Cygnus A, very powerful, well-known radio galaxy. You can see the core, because in the thin arc here, this is the relativistic jet being powered by the supermassive black hole here. It is going and hitting the external environment, and there is a plasma is hitting here and then flowing down. And all along its path, the electrons are getting constantly accelerated. And that is why you're seeing the synchrotron. The highest acceleration is at this point where it's directly hitting the external medium, so it's getting strongly accelerated. You can see that you can make out the beam of charged particles here, but not much here. That's because it's relativistic deboosting. The intensity is decreasing. You can see the spectral maps, etc., etc. And this is the radio spectrum at the hotspot. You can see it as power law to some extent, and then it is dropping off because of curvature. But then there is another curvature here, which has been modeled. Why is this? Two reasons. It could be that the particle distribution itself cuts off at a higher value. So you have the particle integration from gamma 1 to gamma 2. It's a distribution. It can be an effect of the lower limit of the gamma distribution of the particles, or it could be absorption. Something is getting absorbed here, and that is why the emission is not coming towards you. I'll not go into the details of this. So last 15 minutes, because I started 5 minutes late, would be bremsstrahlung, and let's see if I can touch upon Compton. So what I discussed right now is emission from relativistically moving charged particles gyrating along magnetic fields. Now we come back from relativity to non-relativistic systems, non-relativistic thermal systems. What we are trying to understand here, if suppose there is an ion, a positive ion here, and there's an electron passing by, it will feel some bit of attraction between these two. So if it is quite far off, the interaction will be weak. So there is a small deviation in the path of the electron's trajectory. And then the electron will feel some acceleration due to this force from the ion. So bremsstrahlung is a non-relativistic phenomena where we want to study if there is deviations in the path of free electrons streaming around as they interact with a background sea of ions. We first do what we can for a single system, for a single electron ion. Then we have a distribution of ions, distribution of electrons, and that is how you get the actual physical system. Again, I will not sketch the full derivation, of course, but since I don't have time to discuss all this, but again, it's important not to get bogged down in the mathematics, but to understand what is the physical scenario that is taking place here. So that when you do some experiments or try to understand the basics of some of the physical processes, you know this is the basic physics. You can always put the maths in later. So what we essentially try to do here is again find out the perpendicular component of the acceleration and the parallel component of the acceleration. This is the basic game. You want to find out the electric field, and you also want to find out the Fourier transform of the electric field. You can play different tricks and simplify the system according to your wish. So you have to compute this term essentially. So this d dot is just the dipole acceleration term. and you then need to compute the Fourier transform of the electric field. You can rewrite it in terms of the Fourier transform of the dipole component. I'm deliberately going a bit fast because all these details are not essential for you, but just to sketch the basic idea. So how do we do it? We define the dipole term here, which is proportional to the acceleration, and we then take a Fourier transform. Now you get a Fourier transform of the acceleration vector. Okay, these integrals can be computed using Bessel functions. What is important is what comes in the next slide. So after putting all of this in, you'll get some expression for the perpendicular component of the acceleration and the parallel component, all in terms of the Fourier components. You sum these two together, you will get two limits. One for omega tau less than. What is omega tau? Omega is a frequency. So now we're trying to understand the frequency. Omega is a frequency at which you want to observe this radiation. What is tau? Tau is a characteristic time scale. I have skipped this. So this is the impact parameter. So if initially the electron is approaching in this direction, what is the distance between the approach point of the electron and the parallel line drawn from the charge? So that's the impact parameter. And v is the initial velocity of the electron. So typical time scale is b by v. Okay. So that is tau. So for omega tau less than 1, you have some expression over here. For omega tau greater than 1, you have, because this is taken from Longueur. Rybicki gives a more heuristic way of deriving it. I would suggest that you go for Longueur because that's a more mathematically sound derivation if you are more interested in this. The expression is e to the power minus omega tau. Now for omega tau larger than 1, this term drops off and that's why it's 0. So we approximate, we have a limit for which we will observe in radiation given the frequency. So given the frequency, given the velocity of the charge and the impact parameter, we can have the emission like this or 0. Or just to also just recasting it in terms of the limits of v, because it's important to understand what it means for the impact parameter. If the velocity of the electron is fixed and the electron is then approaching the charge at different impact parameters, there is a natural limit of the impact parameter that you must consider. And why this is because it will become very clear in the next slide. So if b is less than v by omega, then you have emission for that frequency. Again, this is v by omega. It depends on frequency. If b is large than v by omega, then you have 0. Okay. What we do next is we assume that there is an ion, there's a sea of electrons. So now in concentric circles around the ion, and sea of electrons all passing in the same direction, impinging on the ion. So in concentric circles around the ion, we can find the total number of electrons that are experiencing the interaction from the ion. Okay, so essentially it's a system like this. One charged particle here, all the electrons passing. So what we do is B, and this is dV, B plus dV. So we take concentric rings and then integrate to get the total emission, something like this. If you perform this integral, it becomes very trivial, and you get something called log of B min and B max. Okay, because what you are doing is you are going, so the sea of electrons is infinite, and you are going away from the location of the ion. So you have some maximum B for which you will get it, and a minimum B, because you have to put the integral limits. Now the maximum B is pretty obvious from the previous slide. You get emission only when B is less than V by omega. So B max is when B max equals to V by omega. That's the upper limit. What do we do for the lower limit? That is a bit tricky. This is where a bit of hand waving comes in. If B is very close, then it actually becomes a scattering. You go and hit the ion directly. But you can have some lower limit to the V. So in the classical case, again, we will take two cases. One is a classical case and one is the quantum mechanical case. I'll come to the quantum mechanical case. So the classical limit is, I prefer this way of understanding it, when the energy of the electron is proportional to the Rydberg energy, Z square by B minimum. So Z square by B is the potential energy, and that is proportional to the kinetic energy of the electron. So that immediately gives you one B minimum value from the velocity of the electron. Other is the uncertainty principle. Delta X, delta P greater than H bar. So we want delta X. P is the momentum of the electron. We get a natural limit to it. The ratio of these two different limits of the B min is V by C. So if the velocities are non-relativistic, you use something. If the velocities are relativistic, you use something. This integral, so essentially this entire formula, the previous formula here, again, it's important to note on what factors does it depend on. It depends on the number density of the electrons and number density of ions, Ne times Ni. And the Z square is the atomic number. Then this stuff inside the logarithmic term. And these constants in front, they will change as we go to a different approximation. But for this particular integral, it depends on the mass of the electron, the velocity, and the charge. So then, for this particular system where we have a single electron and a sea of constantly moving, single ion and constantly moving electrons, the total power as a function of frequency of the spectrum becomes something like this, which is constants in front. All these are constants now. Velocity is constant. It is proportional to square of the density, Ne times Ni. Or you can equate this to n square if the number of particles is same. But N times Ni is a better description. And a factor that depends on the logarithm of the Bmax and Bmin. First of all, we have done some hand-wavy stuff while calculating both Bmax and Bmin. But this is inside the log. Even if we are incorrect due to our assumptions, this does not significantly change the outcome by several orders of magnitude, for example. This term here is called the ground factor. Again, the ground factor is tabulated. If you are working on Bremsstrahlung, go read this review by Novikov and Thorn. And the review gives much more detailed understanding than what is there in the standard textbooks. So what do you do? And this is usually I give in exercises for assignments for different scenarios, so different velocity and different frequency. You can find out where you lie along the x and y axis, and then find out what the appropriate form of the ground factor should be. Okay, this is how you actually compute the synchrotron emission. Now this is for a constant stream of electrons moving with a constant velocity. Now, as I said, this is a non-relativistic system, so it can be a thermal system. This is a thermal radiation. The previous was non-thermal radiation. So if the system is a thermal system with a finite temperature, then of course the velocities will have a Maxwellian distribution, Maxwell-Boltzmann distribution. So what do we do then? It does not have a single velocity. It has the velocity will depend on the Maxwell-Boltzmann, so we integrate over the velocity distribution. But be careful that we have a minimum velocity here now. Why? Because of the spectrum. Because what we want here is the energy at a given frequency. So h nu cannot be larger than half mv squared. So there's a natural limit to the integral over here. You do all of this stuff here, and again, that's why I said don't focus on front constants at that point. You get the total expression for thermal Bremsstrahlung. This is the one that is important. Something like this. Ne times Ni. So essentially, in terms of understanding the units, it's square of the density. And that is what is important, because if the density increases by 2, the emission will increase by 4. That is what is important here. And then there's an exponential cutoff, h nu by kt, and then the ground factor. The ground factor is again integrated over the distribution function, and again Novikov-Thorn has a whole chart of how you evaluate the ground factors. Briefly touch upon what is free absorption. Now, I discussed about Kirchhoff's law yesterday, and I told you that that's a very powerful law, in the sense that if you know the emission coefficient of a thermal system, you can just immediately use this principle and find out the absorption coefficient. What does this mean? We know the emission coefficient of the thermal system. It's a thermal system, so potentially it can be in equilibrium with a black body. If it can be in equilibrium with a black body, then any ray passing through it will satisfy this quantity because it's a thermal system. So if this is true, then again, all I'm talking about is the microphysics of the system. There's nothing to do with the background radiation. Then its absorption has to satisfy this criteria. It has no way out of it because it's a thermal system. And if that is the case, you can immediately write off the absorption coefficient in this way. You just derive what is the emission coefficient for a thermal system. Divided by the black body function, you get the absorption coefficient. Pretty simple. And this is important where for example, the background radiation does not need to be thermal in nature. I just showed you about the jets here. I've removed the slides, but this is something that we did in 2018. So these jets are emitting synchrotron radiation. This is a large jet, this is Cygnus A. There are also smaller jets that are confined within the host galaxy itself. Now, as the synchrotron radiation is passing through the ionized gas in the host galaxy, the ionized gas is in thermal equilibrium with the environment. So that ionized gas can actually absorb this background radiation because the absorption coefficient of that ionized gas is fixed. So that is called free absorption, where the synchrotron, a non-thermal radiation is getting absorbed by a thermal system. And where do we see Bremsstrahlung, or where do we need Bremsstrahlung? For example, in studies of galaxy clusters, just as one example, Bremsstrahlung is everywhere. But for radio astronomy, this becomes very important. Study of or X-ray astronomy, study of galaxy clusters, you see a big halo in X-rays. And this is because there's a wide distribution of ionized plasma going to high temperatures. And this gives you Bremsstrahlung emission. That's one of the dominant emission mechanisms because the temperature is very high. So just to give you again a brief understanding of what are the things it depends on. To remember, the emission depends on square root of T. So this is the spectrum. The total emission will actually depend on square root of T. I see I've removed the slide for the total emission. But the total emission integrated over the frequency will depend on the square root of T and the square of the density. Okay. These are 2 important factors to remember for Bremsstrahlung emissions. And I have just 3 slides. Maybe I'll just take 5 minutes to go through or give you a brief introduction to scattering. So you learned about non-thermal synchrotron, thermal Bremsstrahlung, emission and absorption. Another very important emission mechanism is scattering. And while dealing with scattering, the first thing that we will encounter is non-relativistic scattering of a background radiation by a charged particle, which is Thomson scattering. So in Thomson scattering, it's all non-relativistic motions. We don't have to consider quantum interactions or interaction of consider the emission as a particle. We can consider the emission as a wave. So what we do here is we have an incident background radiation on this charge, and this charge will oscillate along with it because of the electric field of the radiation. And if it's oscillating, of course, then it's accelerating. So we have the standard expressions of the dipole formula, dp d omega, the power distribution, etc. We define something here, which is we have the Poynting flux. So the power per unit solid angle divided by the Poynting flux is the cross section of scattering per unit solid angle. So d sigma d omega. Again, if you remember, this was the cross section that I talked about when I was talking about absorption. But this is scattering cross section. That was absorption cross section. They are similar, but the terms are different. But you can think of it in that context. The cross section over which the interaction is taking place. So if you integrate over all solid angles, you get something like this. It's all a function of fundamental constants. 8 pi by 3 r naught square. R naught is the classical electron radius. So this is the Thomson scattering. Again, very quick and very brief introduction to Thomson scattering. When you have a background radiation, making the charge oscillate, and then you can calculate what is the power distribution and the scattering cross section. Now, what happens if you go to a system that is where the charges have relativistic motion? So this was all non-relativistic. Then you actually have to consider the interaction or a collision of a photon. Now we go from a wave to a photon with the charged particle. So you write down the full four momentum. The four momenta are conserved, of course. And from these conservation relations, you can find the energy of the scattered photon. So what we do here is, this is in the rest frame where the electron is initially at rest. The photon comes and hits the electron and gets deflected in a different direction, and then the electron picks up some energy. That is how you balance the momentum equation. Very standard stuff if you have done special relativity. These are exercises in special relativity. So the final energy of the photon that's scattered depends on the initial energy of the photon, which is epsilon prime, the angle of scattering, and the mass of the electron. This is the formula you get after this algebra over here. Now again, just focus on how the final energy and the initial energy are related and what it depends on. So if the energy of the incident photon is much less than the rest mass energy of the electron, so E by mc squared, E prime is the incident energy, by mc squared is less than 1. The denominator goes away, just 1. So the initial energy of the photon is same as the final energy of the photon. Okay, so this is a case of elastic collision or elastic scattering. So what happens here is approximately only the direction of the photon changes. The energy of the photon does not change in the rest frame of the electron. Things change if you change reference frames. Now consider the electron is moving. You're no longer in the rest frame, you're in the lab frame. And then the photon is moving, so they're coming and colliding with one another, and then the scattering is taking place. We can use the same principles here derived in the previous slide. We go to the rest frame of the electron. As we go to the rest frame, we can use those things that we derived. We can find the final energy, and in the rest frame of the electron, if the incident energy of the photon is less than the rest mass energy of the electron, then the scattering is elastic. So E1 prime is E prime. So now you know what is E1 prime. You go back to the lab frame. This is the final expression you get after some algebra over here, which I've highlighted here. You go back to the lab frame. This is again, just focus on what is the implication of this relation here. So what does this say? This is the incident energy of the photon in the lab frame. This is the scattered energy of the photon in the lab frame. This is the incident angle of the photon in the lab frame. This is the theta. And this is the scattered angle, theta 1 prime. Now, E1 is not equals to E. This is because of the effect of relativity and the way you change the angles. Interesting implications here. One is the head-on collision. So photon and electron are colliding directly head-on. And after the collision, the photon is reflected along with the electron. So theta equals to pi. The initial theta is pi because they're oppositely directed. And after the collision, they are moving along the same direction. So theta is 0. Put this in, you get that the scattered energy of the photon is 4 gamma squared epsilon. Very powerful. What this shows you is if the photon has some energy, its energy can increase by gamma squared. If the gamma of the electron is high, it can have a very large increase in the value of the energy of the photon. So that gives you a maximum energy that can be tapped from the system. Other case, it's a tail-on collision, where the photon goes and hits the electron from the behind. Okay? So in the tail-on collision, after just putting in some values here, you will find that the energy of the electron, and then after the collision, the photon is reflected back. So theta equals to 0 now because they're moving in the same direction, and theta equals to pi after the scattering. Put this in, you'll find the energy of the photon is epsilon by 4 gamma square. Now the electron has gained energy and the photon's energy has decreased. So this is the lower limit of the scattering. This is just a cartoon picture of where you see scattering phenomena. For example, if you want to study emission from accretion disks, emission from the accretion disk will then get scattered by a halo of highly charged, high temperature electrons surrounding the accretion disk and the black hole. So this is a black hole in the center. It's called the corona. So the soft photons, the thermal photons from the accretion disk get scattered in the corona, and then it forms an extended power law tail with an exponential cutoff. You can also have reflection, etc., etc. So this is a standard application of the scattering process. Many such applications. I don't have time, unfortunately, go beyond this. So the key takeaway point is what you need to understand. So this is the last line. I don't have anything else. So key takeaway point is what you need to understand is what is the nature of interaction for these different physical processes that is giving rise to the emission, whether it's relativistic, non-relativistic, whether it is the energy of the photon is close to the rest mass energy of the electron. If it goes beyond the rest mass energy of the electron, then quantum mechanical effects start to come into play. So then the simple cross sections that we used will no longer be valid. So I'll end here. Any questions? This was a lot of information packed into 1 hour. I'm sure you have grasped only a fraction of it. But I guess as you hear more about this in subsequent applications, as you learn, you'll get a feel for things. If you have questions, you can pass it on to the organizers and we can address them. Okay? Thank you.
What is the signature of a synchrotron radiation from observation point of view?
What do you mean signature?
Means how we understand that this is a synchrotron. Suppose we are seeing some radiation. Okay. So what will be a signature? Is polarimeter? We have a polarimeter and we are observing if there is polarization or something like that.
Yeah. So sorry, I've turned off my mic. So your question is, what is the signature of synchrotron emission? Now, synchrotron, when we observe radiation, we do not know exactly what is the source of this radiation. Synchrotron radiation can also be in frequencies where we observe standard thermal radiation. So as I discussed yesterday, one thing would be immediately to check the brightness temperature. It can still be synchrotron radiation. Then comes into the physical modeling of where this radiation is coming from.
That you have shown the power law spectrum.
Yes.
The power law.
Yes, and then you get the spectrum. If the spectrum is a power law, then it is probably a non-thermal spectrum. Okay, and then we can then make some models of what is giving rise to non-thermal electrons. You have a non-thermal distribution of electrons giving rise to this, and so then is to magnetic field and relativistic electrons. Then you have to put in those values of the gamma 1, gamma 2 to see whether your spectrum matches with the observed spectrum. So spectrum, the brightness temperature. In brightness temperature immediately gives you what is non-thermal or thermal. And then the spectrum, you observe it at different frequencies and then find out.
Any power law index range?
Yeah, so power law index for different systems have been classified. For example, for extragalactic sources, the typical index is around average of -0.6. For blazars, it is slightly flatter. So the core of the galaxy is slightly flatter. So all these have been tabulated and well studied now. Any other questions? Yes.
So what is the typical time scale of this synchrotron radiation? Like you showed that as the electron revolves, we get for a certain time period and then pulse and then stop. And then
That's right. But that is for just one gyration. So the electron is gyrating continuously. So you'll get a continuous train of pulses. So just from the gyration, it is not a wise choice to understand a time scale. When you talk about time scale of the synchrotron radiation, the more relevant question would be, if you have a physical system that is giving out synchrotron radiation, till what time will it continue to give on synchrotron radiation? Okay, so that would depend on whether the electrons remain relativistic or not, because the electrons are cooling down. So all this jet stuff that I showed, you're not seeing synchrotron radiation from here and here. Although there probably is electrons flowing down here and coming here. There is still magnetic field. If there is emission here which has magnetic field, there is magnetic field here as well. But you're not seeing synchrotron emission here. Why? That is because for this particular frequency, the electrons, the critical frequency is such that, so critical frequency is proportional to gamma square. So the gamma of the electrons are such that at that particular frequency, when the critical frequency has been pushed to lower values. So there's a finite cooling time scale of the electrons that also gives you the synchrotron time scale. So that's called synchrotron cooling time scales. You take the total synchrotron power, this, you take the total synchrotron power, and then divide it by the energy of the electrons. That gives you a typical time scale of the synchrotron. I think that is a more relevant question.
But if we like have a number for 2 pi by omega b.
Yeah, but that is a continuous strain. So this pulse that I showed you, it is very fast rotation because it's all relativistic, no? And you are seeing an average distribution of electrons and pulses. You are not seeing just one electron. I'm talking about astrophysical sources. You can always design a very unique system with just a single electron. So theoretical calculations you can perform. This one single electron and the time scale would be just this pulse width. But that is not what we are seeing. We are seeing a distribution of electrons, all with different orientations, and going through different regions with different magnetic fields as well. Any other question? Okay, so then we can,
If nobody has.
Yeah. Okay.
This integration of the analysis, this analysis is perpendicular to the
Perpendicular to the velocity. Yes, that's right.